Good morning, everybody. My paper is actually kind of similar along the lines of what Kieran just did, but it transfers over to aluminum 12 silicon. This picture is actually a picture of the thermal conductivity, it's called, unit they used, and I'll get to that in a little bit. The paper was called Laser Processing of Bulk Aluminum 12 Silicon and the Influence of Microstructure on Thermal Properties. The study was done in 2011 at Washington State University, and it was posted in the Philosophical Magazine, which I thought was interesting. Um, uh, and the scope was, sorry, it's not correct up there. It was to analyze the microstructure and the thermal conductivity of the process parts using LENS, which is laser emanating net shape manufacturing. And the key questions were to see how the microstructure features affected thermal conductivity and how this compared to conventionally cast components. So they made little cylindrical components. They'd cast some, and they made some using the lens process, and they were 12 millimeter diameter by about 20 to 25 millimeter height. And once again, they used the aluminum 12 silicon. They discussed why they chose it. They chose it because it was kind of the optimal density of silicon, because silicon has a much higher melting point and much higher laser absorption than the aluminum. So this combination was kind of best for the laser process. And they examined the laser power, the scan speed, the specific energy of the laser, the relative density of the parts, and the microstructure and the thermal conductivity. And they analyzed the microstructure using a scanning electron microscope, and the nanoflash tool was the picture on the first slide, which they used for thermal conductivity. So the first thing they discussed was optimizing the laser and for the scan speed and the energy power for the silicon in the aluminum. And then, as you can see from the different pictures, varying the scan speed and the laser power has a pretty significant effect. And actually, they didn't actually show the optimized laser power. These are kind of the three different types of errors that they could produce. A is the low power, and they called it almost like a bubbling effect, where the surface tension of the gas is higher than the surface tension of the solid when it's interacting with the liquid metal. So it kind of like water droplets, it forms little spherical bubbles, and it can, as you can see, it gets even bigger when they increase the laser power a little bit. So it gets more power at the center and less power as it expands out. So it has more opportunity to form the droplets and doesn't solidify very well. And then when you have another layer that comes on top of that, it produces porosity, which is very undesirable. And then part C is when they increase the powers even more to their maximum of, I think they tried 500 watts was their maximum power, and it produced too much spreading, so you can see it kind of washes around and doesn't produce a clean surface. I kind of wish they would have shown what the optimal surface was, but they didn't show a picture of that. And they determined that because of the high melting point of silicon and the high laser absorption in comparison with the aluminum, there was a very small window they had to work with as far as laser power and scan speed. And for the three different laser powers shown in the table, those are the optimized parameters for each one. And that was the best density they could get for each power. And they did do tests on multiple samples as far as thermal conductivity for each of those densities. So the next thing they wanted to analyze was how does lens affect the microstructure in comparison with the casting process. So when you use a laser process, there's a rapid cooling that takes place when the laser moves away from the surface, and that doesn't happen in a casting process. It cools much more slowly, even when you have a rapid cooling system applied on the casting. And as you can see, sections A and B are from the casting process, and the rest are all from the different lens processing. So you can clearly see the silicon. They call it bulk fibers, kind of, that show up when you use the casting process. Whereas even with different laser powers, they really don't show up. And it kind of as it cools, the silicone cools in almost like a snowflake pattern, where it just kind of spreads out. They call it a dendritic structure. And they noticed, you can see, even this is a 5 micrometer picture, the silicon features are considerably smaller compared to the 20 microns of picture B, which is very desirable as far as thermally conductive properties. So in studying the thermal conductive properties, they noticed that no matter what processing method you use, thermal conductivity increases with temperature. And as you can tell, the diamond-shaped patterns at the bottom of the graph on the left are the cast sample, which is significantly lower. They said between 20 and 30% lower than what they could get from the lens process. And although the laser process materials have a lower density, the density of casting is up to 98%. They said that the microstructure effects outweighed the lack of density. They compensated and gave superior thermal conductive properties in the aluminum. And they also said that even though they used aluminum, this could be applied and extended to any other immiscible compound alloy. So in summary, the laser processing of the lens manufacturing process significantly enhances the thermally conductive properties of aluminum 12 silicon. And lens can be used effectively to change microstructural features of any immiscible alloy as long as it can be melted with the laser. I thought this was a really well-written paper. They really explained what they were saying, and if they had an explanation or a reasoning based on it, they cited a paper, but they also explained what the paper said, which I thought was really helpful. And I would like to see it extended to many different alloys, kind of like what Kieran was talking about with the Inconel, see how that would affect the density and that type of thing.